Hello everybody, CRS here. Hope everybody is doing great. In this video, we will be discussing the center of mass concept and how to calculate it for various bodies. Now let's find out with the first concept in center of mass. What is center of mass of a body? Now, center of mass is a point at which all the mass of the body is assumed to be concentrated at. So then is it a mathematical thing that we really do? No, it's something that exists really, and universe takes the center of mass very seriously. How to locate the center of mass of an object? I've just got a quick demo to share with you. I have a regular PVC pipe here, and it's a hollow cylinder, and hence if you ask me how to find the center of mass for this object, you would want to, let's say, imagine this center of mass to be exactly at the center because it's a regular body. Now that's how one calculates the center of mass. But let's say that this was not a uniform rod, it was a non-uniform rod. That means different parts of the rod weighed by different amounts. Then the center of mass would not be exactly at the center. Wherever the center of mass of the rod is, assuming that the gravitation at all of these points, gravitational field at all points is the same, then center of mass and center of gravity would coincide. If you want to figure it out, you would try to balance it. Wherever it gets balanced, that's where the center of mass is, right inside the rod. So if you try to balance it, it will fall down in various ways. The easiest way to get to the answer, get to the center of mass, is simply by sliding both of your hands one closer to one another, and you will find that the center of mass is right here. So the center, it's quite easy to figure out center of mass of bodies like this. Quite easy to calculate it also. So here is the balance point, and that's where the center of mass of the body lies, right at the center. Now, having shared that with you, I told you that it's a very specific point for a given body. This center of mass of a body can either lie inside the body or it can lie outside the body. For example, if you take a sphere, let's say you take a sphere, here you've got a sphere, the center of mass of that sphere would be exactly at the center of that sphere. If it's a uniform sphere, it would be at the center of the sphere. So the center of mass is a point for this body inside it. But then let's say we've taken a ring. If you took a ring, something of this sort, that's a ring. Now the center of mass would again lie here, which is not inside the body anymore, it's outside the body. So center of mass of the body can either lie inside the body or it can lie outside the body. With this particular understanding, we can go further and try and talk about calculation of center of mass, how to calculate the center of mass for discrete mass distribution. Let's try and understand. Let's go to the next bit of understanding. So here is the expression for center of mass for a discrete mass distribution. Now these are the expressions to calculate the x coordinate of the center of mass. Now we know that center of mass is a single point for a system of masses, for a system of particles. If m1, m2, m3 are all particles masses, they are all particles here, all m1, m2, m3 are all tiny particles, and x1, x2, x3 are respective coordinates of these particles, then the center of mass is given by m1 x1 plus m2 x2 plus m3 x3 and so on, divided by m1 plus m2 plus m3 and so on till mn. The same follows for y coordinate as well as the z coordinate. It's as simple as that. So center of mass of any system consisting of many particles can be calculated using these formulae. Let us try to solve one question that had appeared in a competitive exam. Here we go. Masses 8, 2, 4 and 2 kg are placed at the corners ABCD respectively of a square ABCD of diagonal 80 centimeters. So you need to understand that the diagonal here is 80 centimeter. 80 centimeter is the diagonal of the square. That's the diagonal and it's 80 centimeter long. When that is the case, the distance to the center of mass from A would be, from A is in this case the origin, and you need to calculate the distance to the center of mass. Because here there are only two dimensions, x axis and the y axis are the two coordinates. If you find xcm and ycm, that would be more than sufficient. So for calculating xcm, you will need the x coordinates of all the masses and the masses themselves. So let's list all of them down. M1 is this one, A, which is 8 kg, and then X1 is 0 because it is at the origin. Y1 also is 0 because that's the coordinate of the origin. Similarly, you can figure out what is M2. M2 is 2 kg, and that is point B. The x coordinate of point B, you see, is this length AB. Now, if you look at this right angle triangle ABC, then you know the hypotenuse, which is 80 centimeter, using trigonometry, because this is a square, the corners ABCD of a square, the question says. This is going to be AC cos 45. AC is 80 centimeter, that's the diagonal. So cos 45 is 1 by root 2. You can simply write this distance AB, which is the coordinate of the particle at B weighing 2 kg, as 80 divided by root 2, because cos 45 is 1 by root 2. Y1 is 0, the Y2 is 0 because it is on the x-axis and the y coordinate of such a point would be 0. Let's calculate what is M3 now. M3 is the particle at C. You can write that as 4 kg, and X3 is, by the way, this distance, and Y3 is that distance. So both of them are 80 by root 2 and 80 by root 2. X3, Y3 are both 80 by root 2 because this is cos 45 and this is 80 sin 45. So both of these are this way. Everything is in centimeter. I wouldn't be writing the units there, but then it's all understood. M4 is equal to 2 kg and X4 is 0 because it's on the y-axis, and Y4 is equal to 80 divided by root 2. 80 divided by root 2. Now, having understood this, we can now calculate the center of mass. Let's apply the formula. Let's apply the formula for center of mass. XCM would be equal to M1 X1 plus M2 X2 plus M3 X3 plus M4 X4 whole divided by M1 plus M2 plus M3 plus M4. Now that's how you calculate the center of mass. When you do this, you have M1 being 8 kg, X1 is 0, M2 is 2 kg, X2 is 80 divided by root 2, and then we have M3, which is 4 kg, X3 also is 80 divided by root 2, and M4 is 2, and X4 is 0 divided by M1 plus M2 plus M3 plus M4, that's 8 plus 2 plus 4 plus 2. Now that's how you would calculate. 8 into 0 is 0. So this is 160 by root 2, and 4 into 80 is 320 by root 2. The whole thing would be 480 divided by root 2, whole thing divided by 4, plus 8 is 12, 12 plus 4 is 16. So the answer you would have is 30 divided by root 2 centimeter. Now that's the x coordinate of the center of mass. So we have found the x coordinate of center of mass. Here in the question there is x comma y. The coordinate, x coordinate, xcm of center of mass has been found. A similar thing can be done for the y coordinate. Let's try to do that. We have the y coordinate of center of mass being given by ycm, that's equal to m1 y1 plus m2 y2 plus m3 y3 plus m4 y4 whole thing divided by m1 plus m2 plus m3 plus m4. That's how you would figure out the center of mass for the y coordinate. And you will see after substitution, you have all the masses and all the y coordinates, and you will see the answer is going to be similar, which is 30 divided by root 2 centimeter. Now we have found xcm as well as ycm. So we have found both xcm and ycm. All that we have to find now is the distance. Now how do you find that distance? Quite simple here. Look at this. The distance can simply be found by calculating this r. You can use distance formula, or if you can just write, let's say the distance r equal to root of x cm square plus y cm square, you will have the answer. You will have the answer. So we have r being equal to root of 30 divided by root 2 the whole square. So we have a root of 30 divided by root 2 the whole square plus 30 divided by root 2 the whole square. So the answer you would have is 30 centimeter. Now that's the distance to the center of mass. That's the distance to the center of mass. You will see that option B is the correct answer. That's how you would solve the problem if the problem is based on a discrete mass system. Well, now what if the mass there is not discrete? Discrete meaning distributed in a manner where there are tiny particles and are at a specific location, just like in this question. What if it's not like that? What if it's a continuous body? A continuous body like a rod or like a sphere? It's quite simple to imagine all of this, because in case, let's say you have a rod, it's a uniform rod. If it's a uniform rod, let's say something of this sort, that's a uniform rod. You can say that the center of mass of this uniform rod lies exactly at the center of the rod. Now that's where the center of mass is. And if there is a sphere, let's say you have a sphere, that one, and I ask you where the center of mass for such an object is, you would say, sir, again at the center. So if the bodies are uniform and they are symmetric, then it's quite simple to say where the center of mass of the body is. It's at the center, geometric center of that body. But then the question is, what if the center of mass is not symmetric? What if the body is not symmetric? How to find the center of mass of such bodies? That's exactly what we are going to explore in this part of the video. The center of mass for a continuous mass distribution. That means if a body is made of a mass that's located at various places inside it, and it's an extended body, it's not a point mass, then how do you calculate the center of mass? These are the set of formulae. I've just transformed that algebra to calculus out here. So xcm of the body can be written as 1 divided by m into integral of x1 to x2 of x dm. The same thing can be written for each coordinate. So we have xcm, we have ycm, and then we have zcm, and for all of these you can calculate the center of mass. Sir, we have the formula now. We have the formula now, but how do I calculate it in a real life situation? Because an integration here is not like a math integration where you have the variables and then you simply integrate it. You will have to apply a lot of physics out here. So let's try a question. Calculate the center of mass of a semicircular disk. Let's assume that here is where the origin is. That's where the origin is. And I have a semicircular ring here. If it was a complete ring, you could have said right away that the center of mass lies at the center. But now, it's quite understandable that half of the ring is all that exists. The other half is gone. In such situations, where do you think the center of mass of the disk is going to, ring is going to lie. I'm sorry, I said disk, it's a ring. So here is where you can guess the center of mass could lie. Let's calculate that. The YCM is where the center of mass could lie. Well, having said that, maybe I'll mark the YCM here, YCM. It'd be easier for me to write everything else. How to calculate the center of mass for this particular body? We'll write the formula. The formula is that YCM is equal to integral 1 by m into integral of y1 to y2 of ydm. Now question is, what is y? Y is the y coordinate of this mass dm. Y is the y coordinate of that mass dm. Because sir, why did you not calculate the x coordinate? The x coordinate is 0 because it's a symmetric mass. How much ever mass is there to that side is the same mass distribution that's there to this side. So the center of mass of the x coordinate would simply be 0. So that's where the x coordinate would lie, and that's where the y coordinate would lie. So x and y coordinate would be situated somewhere there. So we quite directly know that the xcm is equal to 0. The only task is to calculate the YCM. So I shall take a tiny bit of this particular ring. Let me call that tiny bit dm. Dm is an infinitesimal mass. And to that place, let's draw two radii to calculate the angle between them. And the angle between them is, let's say, d theta. That angle is d theta. This angle is theta, right? And if that's the situation, if you calculate what is the y coordinate of this particular center of mass, this particular element, then it would be this. That's the height, that particular element. If that is the case, then let's assume that the radius is r. Then this much should be r, because this is theta. To this side it's r cos theta. To this side it's r sin theta. So it's r sin theta all the way from here to here. Now, having understood that this y coordinate or that tiny bit of mass is r sin theta, we can substitute it here. But before we do that, let's also figure out what is dm. Dm is that tiny fragment of that particular semicircular ring, and it can be written as total mass of the ring, which is m, divided by total length across which that mass is distributed. You see, it's half the circumference, so you can write it as pi times r, multiplied by the mass, multiplied by the length of this particular dm, and the length can be written as a dl. dl is the length across which this dm is distributed. And by a tiny amount of knowledge of trigonometry, you will know that dl is simply r multiplied by d theta. Arc length is equal to radius times angle. So if you substitute that there, we will have dm equal to m divided by pi r multiplied by r times d theta. R times d theta, r and r gets cancelled. We can substitute all of these things here. I have YCM, y coordinate of the center of mass, being equal to 1 divided by the total mass into integral of y. In place of y, you can write r sin theta, and in place of dm, you can write m divided by pi into d theta. Well, you see, m and m gets cancelled. We are integrating theta. Theta is the angle made by the infinitesimal mass out there, and that infinitesimal mass is present all the way from theta equal to 0 to theta equal to pi, which is 180 degree. Now we are writing it in radian, so it starts from 0 and it goes up to pi. All that there is a little bit of integration to be done. So YCM, let me form the integral for one time, and then we have integral of 0 to pi of sin theta d theta. Let's integrate this. We have 1 divided by, there is an r also, missed that r divided by pi into Integral of sine theta is minus cos theta, and it has to be evaluated between 0 and pi. When you evaluate this, you will have minus r divided by pi multiplied by cos of the upper limit, which is pi, minus cos of the lower limit, which is 0. Cos pi is minus 1 and cos 0 is 1. Minus 1 is minus 2. Minus 2 into minus 1 would give you plus 2 r divided by pi. So now we understand that finally the y coordinate of the center of mass of a semicircular ring is 2r divided by pi. It's an important result. If you derive this for yourself, and not just once, a couple of times, so that this thing sits in your head, this particular formula will come in handy in various examinations. So I would want to appeal to you to request you to do this by yourself a couple of times. Now we know how to calculate the center of mass of a ring. Let's also try to calculate the center of mass of a disk using this result, and that's how we build. We know one elemental result, you build that for a more complex body. Let's try to understand how to calculate the center of mass for a semicircular disk. I want you to imagine this disk to be made out of smaller and smaller rings piled up on one another like that. And you should imagine an onion which is cut in, you take a transverse cross section of an onion and then cut that again into two parts. You will get something like that. You will see the onion rings, semicircular rings, arranged this way to get a disc. I want you to imagine that way so that you'll be able to solve this problem. Let's calculate the center of mass of the semicircular disc. Quite easy, a job to do. Let's take an elemental ring. So here, and that's a tiny part of a ring. So that's a ring. Let's assume that this ring is at a distance small r. That's small r. And if you ask me what is the mass of that ring, mass of that part of the ring, just shade that. Mass of this part of the ring, my dear friends, is dm. Dm is the mass of that part of the ring. When that is the situation, you ask me what is dm in this case. Dm in this case would simply be equal to the total area. Total area would be total mass, which is m, divided by total area, which is pi r square divided by 2. So 2 is in the denominator of the denominator, goes to the numerator. That's dm's fraction, total mass by total area, multiplied by the area of the shaded part of the ring. Now the shaded part of the ring can be imagined as a triangle that's bent in the form of a semicircle. Listen to me again. It's a rectangle that's bent in the form of a semicircular ring. If that is the situation, then there is a length and then there is a breadth. The length, in order to calculate the area, this is total mass by total area multiplied by area. In order to get the area of that shaded portion, the length is pi r, because that's half the circumference. That becomes the length of the rectangle, multiplied by the breadth. If from here to here it's r, from here to here it's r, one step ahead it's dr. So we have 2m divided by pi r square. This r is the actual radius of the disk, and this small r is the radius of the elemental ring that becomes a part of, that's a part of that disk. So having said that, we have pi and pi getting cancelled. Then we have the y coordinate of this elemental ring, because we will need that. We know the formula. We will need both y and dm in order to integrate. From the previous result, we know that the y coordinate of the center of mass of a semicircular disk essentially is 2 by pi times r, where r is the radius of that ring. Okay, so it is 2 by pi times r. Now the formula says that ycm is equal to 1 divided by m, which is the total mass, into integral of y1 to y2 of ydm. Let's figure this out. We have ycm equal to 1 divided by m multiplied by, okay, let me write it a little down here. Ycm equal to 1 divided by m into integral of y1 to y2. We'll figure out what is y1 and y2. Y anyway is 2 divided by pi times r, and dm is 2m divided by r square multiplied by r dr. Well, we have m and m getting cancelled. Push this a little up. ycm becomes equal to 2 by 2 into 2 is 4. So we have ycm being equal to 4 divided by pi r square, because that's also a constant, into integral of r square dr. Now the question is, where does this r go from? If you just look at this, sorry, okay, you just look at this, you will find that this particular r changes from r equal to 0 to r equal to capital R. So let's write that limit. The limit would be 0 to capital R. Even here, 0 to capital R. Let's integrate this. Quite a simple integration to deal with. We have 4 divided by pi r square into integral of r square is r cube divided by 3, r cube divided by 3, evaluated between the limits 0 and r. So all you have is 4 by pi r square multiplied by 1 by 3 into r cube minus 0 cube after evaluation, upper limit minus the lower limit. You'll see r cube and square has a simplification out there, and with that you will have ycm equal to 4r divided by 3 pi. Now this is the formula for center of mass of a semicircular disc. This particular problem teaches us how to build from one center of mass, knowing one center of mass, how to build the center of mass another object. So in order to just write it below the question, I would say that ycm in this case is 4r, okay, cm is equal to 4r divided by 3 pi. That's the center of mass. Of course, xcm would, even in this case, be 0. Well, that's how the center of mass of various bodies is to be calculated. The next question you should ask me is, Mr. CRS, should you really calculate the center of mass for all solid bodies also like this? We have been dealing with different laminae because they are all two-dimensional bodies. You can similarly do integrations and get the answer for three-dimensional bodies, but then to cut down the amount of pain that you go through, I have listed the most important formula for center of mass, and here it is. For a hemispherical shell, the y coordinate would simply be r divided by 2, so it's half the radius. For a solid hemisphere, it's 3r by 8, taking the origin to be the center of the complete sphere. All of these facts have been listed for you. These formulae will prove to be very helpful in different competitive exams, so you make sure that you write them and practice. If you write once, it's as good as reading it 10 times. So cut your effort down, write it, and then practice. You should improve by leaps and bounds. Let's look at the last question for this video. In this particular question, a circular disc of radius r is removed from a bigger circle. So what we have here is a circle. That's a circle, and then let's have this thing shaded. That's where the center of the circle is. Here is the center of the circle. The question says, it's a disk. It's the radius of this disk is 2r. So let's try to draw the radius of this circle, and the question says that it is 2r. That's 2r, such that the circular disk of radius r is removed from a bigger disk of radius 2r. So this is the bigger disk. A smaller disk of radius r is removed from it. So let's do that bit. So you have to remove this particular part of the disk. So I think we will do this. Yes, I think we've got to remove this. So I have removed that part. The radius of this removed part of the disk is r, the question says. The circumferences of the disks coincide. So you see that both of these disks coincide. Locate the center of mass of the new disk from the center of the bigger disk. So from the center of the bigger disk, which is here, you need to find the location of center of mass. So let's try to figure out where the center of mass of the bigger disk could be when this mass wasn't removed. So when this wasn't removed, you see the center of mass of this disk was exactly here at the center. But then when you remove it, the mass of the disk comes down. At this place, the distribution of mass is gone. So this part of the mass is gone. So center of mass will shift to that place where when the body is more massive. Well, that means this part in this particular disk, this part of the disk is more massive. So the center of mass would shift to this place, somewhere there. Then how do you calculate the center of mass at that point? Quite simple. If you ask me how many bodies are there, if you answered, you would say, sir, there is one body, which is the cut disk. I would say there are two bodies. A body here, which is a complete disk, a body which is a complete disk here, and then there is a disk of negative mass, and that is being placed like this. So positive mass and negative mass get cancelled, and then you have nothing out there. That's how you would imagine. So there are two masses. One disk of mass capital M, okay, one disk of mass capital M, and the other disk, which is this is only a mathematical concept. There is no such thing called negative mass, but then we will write the smaller mass M, which is the mass of the disk here. We will assume that to be negative mass, so that positive and negative would cancel out each other in this part and give you a 0. That means that part is removed. Capital M, which is the total mass of the disk, is M. Small m would be equal to the mass of this part. How do you calculate that? Total mass divided by total area, which is pi r square, multiplied by the area of the smaller disk. I'm sorry, the pi r square would be 4 times pi r square, because the radius of the bigger disk is 2r. So pi into 2r the whole square is 4 pi r square, multiplied by the area here. The area here is pi r square. I'll have pi r square and pi r square getting cancelled. Mass of the cut part of the disk is 1/4 of the total mass of the disk. So that's how you figure out how much is the cut part of the disk. Well, with this, if you ask me, of course, the y coordinate of the center of mass here would be 0. It's symmetric. This part of the body is a mirror image of this part of the body, and hence the y coordinate would be 0. It's only the x coordinate that would change. That's your origin. Oh, we will have to figure out where the center of mass is. Of course, you've chosen that to be the origin. So that side it's positive x, this side it's going to be negative x. Let's figure out. M1 in this case is equal to capital M, which is the complete disk. M2 is the negative mass disk, which is minus m by 4. x1 is the center of mass of the bigger disk, which is at the origin, so that's 0. And the x2, which is the x coordinate of the negative mass, is here, which can be written as r by 2. I think it's time for us to use the formula and get to the answer. Let's get to the answer. Well, we have xcm equal to m1 x1 plus m2 x2 divided by m1 plus m2. So we have xcm being equal to m1, which is capital M, x1 is 0, plus m2 is minus m divided by 4 multiplied by r. Because I'm sorry, I wrote r by 2 here, but it should be r because it's not half the radius, it's actually just radius r, divided by the total mass, which is m minus m by 4, that's 3m by 4. Let's work this out. You will have xcm being equal to m and m would get cancelled, and 4 and 4 also would get cancelled. You will have r divided by 3 with a negative sign, which means the center of mass is onto the negative x-axis, on the side of the negative x-axis, and is at a distance of r by 3 from the origin. So r by 3 from the origin, the center of mass is located to this side. Why did it come here? Because the mass went missing. If the mass was there, then the center of mass would have been here. The moment you remove it, the center of mass goes to the place where the larger mass is situated. It shifts to that side. With this insight, if you practice these, this would be a very good introduction for understanding and solving problems with respect to center of mass. I think we have solved variety of questions. You practice this and you will have a way to go. It was great talking to you in this video. I'll be back with another signing off CRS for the day.